Hello and welcome. In this problem, an object undergoes an acceleration which is given to us in component form, 2.6 x hat plus 3.8 y hat meters per second squared for 10 seconds. And we are given the velocity also in vector form, the final velocity, as 30x hat plus 17y hat meters per second. So we have four parts to this question. A, what was the initial velocity in vector form? B, by how much did the speed change? Now the speed is the magnitude of the velocity, if you recall. C, by how much did the direction change? And D, show that the change in the magnitude of the velocity vector does not equal the magnitude of the acceleration vector times time, and why. So there are multiple steps here, and what we want to remember is smooth is fast. So we're going to take our time and use the idea problem-solving format to get this done.
With God's help, you can do physics
a
boss as you are created.
You are created in God's image.
To be fruitful and multiply.
Fill the earth and subdue.
Do it.
The first step in the idea problem-solving format is to interpret, which usually starts with some sort of a picture. So we are given the final velocity in component form of x hat and y hat on the axes, and we've got some initial velocity. Our final velocity, we are told, has components of 30 in the x direction, meters per second, and in the y direction we have 17 meters per second. Now clearly this is not to scale, however, it helps us in our setting up our problem. So the general principle of physics here that we're going to be applying are twofold. One is a vector notation and acceleration kinematics. Next, we're going to develop a plan. That's the D part of the idea problem-solving format, which will be our approach to evaluating the problem in the next step. God has crowned you with glory and honor.
Honor to rule over his creation.
The steps we're going to employ: first, we will write the given final velocity vector and acceleration vector in component form. Then we'll write the kinematic equations in component form. Then we're going to solve the x equation, the x component, for the initial velocity vector's x component. And similarly, we're going to solve the y equation for, go ahead and use our x hat notation and y hat notation. We're going to solve the y hat equation for the y component of velocity. And then we can compare, which was one of the purposes was, we're going to compare the magnitude of the initial velocity vector and the final velocity vector. And we're going to show, or we'll use that then to compute the difference. So the change in the magnitude of the velocity is going to be equal to the final minus the initial velocity vector. Okay, so that's part of the problem. Now we still have a couple more steps to go. The initial angle, theta naught, and the final angle, theta final. Finally, we'll compute the magnitude of the acceleration vector, and then we can show the final part of the problem, which is that the change in the velocity vector magnitude is not equal to the acceleration vector magnitude times time. Science is a gift from God
to help us master nature,
but sin added thorns and thistles,
requiring the sweat of your brow to succeed.
Now that we have a plan, we can go ahead and execute the problem. So first of all, we are given that the final velocity vector in the x direction is equal to 30 meters per second. And the final velocity vector in the y direction is equal to 17 meters per second. The acceleration vector in the x direction is equal to 2.6 meters per second squared, and the acceleration vector in the y direction is equal to 3.8 meters per second squared. Now let's write down our kinematic equations in component form. The final velocity in the x direction is going to be the initial velocity in the x direction plus the acceleration in the x direction times time. Similarly, the velocity in the y direction, I should have conserved space better. The velocity in the y direction, final velocity, is going to be equal to the initial velocity in the y direction plus the acceleration in the y direction times time. So you'll notice these equations are essentially the same, they're just isolated to the x and the y directions so that we can work separately and then put it back into vector form. So then we can solve each of these equations for the quantity that we're actually looking for, which is the initial velocity, is going to be equal to the final velocity minus the acceleration in that direction times time. And similarly for the y direction, this will be true in each component. Okay, so now we're ready to substitute in the given values because we have these. We have the final velocity values in each component and the final acceleration values in each component. So let's sort of divide this as we work. So working in the x direction is going to be equal to 30 meters per second minus, in the x direction, 2.6 meters per second squared times 10 seconds. And that comes out to be 4 meters per second. Oops. And that comes out to be 4 meters per second. And similarly, the initial velocity in the y direction is going to be equal to 17 meters per second minus 3.8 meters per second squared times 10 seconds. The time is the same for both of those, and we compute that to be negative 21 meters per second. Now, if that seems a little bit odd to you, it's okay. We have our graph here at the beginning and interpret. We have our positive x hat direction and our positive y hat direction. So if we come up with a negative value, that just means it's going in the opposite direction to the one that we designated as positive. So that's not necessarily a warning sign yet that you've done. Learning physics
Often requires prayer
as we submit
to Jesus Christ
as risen
King of Kings and Lord of Lords.
Okay, we're continuing to evaluate this problem. We're still on part A, but don't worry, it's equipping us for the other parts. Part A asked us to find the initial velocity vector. What we've done so far is find the components, and now we will express that answer, the initial velocity vector, in terms of each component. So we determined that the x component was 4 meters per second in x hat, and then plus our y component, which was actually negative, sorry. So plus a negative in the negative direction, 21 meters per second y hat. Now you can also express that, your instructor might want you to express that as a vector this way, as 4 comma minus 21, and then the units afterward, meters per second. So now how do we compute the magnitude of that velocity vector? We use the Pythagorean Theorem. So the magnitude here of the initial velocity vector is going to be equal to 4 squared plus we'll just put negative 21 squared. You can see that that's going to all be positive anyway. And that is going to be equal to 21.38 meters per second. And then if we compute the magnitude of the final velocity using the initial values we were given, similarly, we'll have the square root of 30 squared plus 17 meters per second squared, and that turns out to be 34.48 meters per second. And so if we then can compute, very simple, now we're back to arithmetic, the change in the magnitude of the velocity vector is equal to 34.48 minus the magnitude of the initial vector, and that gives us a final value of 13.10 meters per second. All right, so that's our change in speed. See, we went from A to B pretty quickly there. Now we need to figure out the change in direction. I'm just going to go ahead and write that here because we're about to change. It's going to look like we're going to change some notation, so don't get mental whiplash here. So the initial angle is going to be the inverse tangent of the y component over the x component of velocity. So we're going to have minus 21 meters per second over 4 meters per second. And that's going to give us an angle of negative 79.22 degrees. Now again, the sign here is telling us a direction, so it's okay. And if we find the final angle, we will have the inverse tangent of the final y component of velocity, or y component, of velocity over the final component of the x velocity, and that's going to give us an angle of 29.54 degrees. So if we think back to our drawing, a positive angle is going to be going from the x-axis up toward the y-axis, and a negative angle would be going, so in the counterclockwise direction, and a negative angle would be moving toward in a clockwise direction, just to help you picture that in your mind. So the change in the magnitude of the angle is the final angle here, 29.54 degrees, minus the initial angle, which was a negative. We need to keep track of that, 79.22 degrees. And so our total change in angle is 108.76 degrees. So that's the change in direction. That's part C. Moving on to part D. Let's move over to the other board so we have some more room here. Now we were asked to compare y in part D. We were asked to show that the change in the magnitude of the velocity does not equal the magnitude of the acceleration vector times time. So we haven't computed the magnitude of the acceleration vector yet, so let's do that next. The magnitude of the acceleration vector is equal to, again, applying the Pythagorean Theorem, 26 squared, the x component, plus 3.8 squared, the y component, and that's meters per second squared. And we're going to take the square root of all that, which gives us, oh, I take that back. The magnitude of the acceleration vector times time is equal to, applying the Pythagorean theorem again, the x component of the acceleration, 26 squared, plus the y component squared, 3.8 squared, and that's meters per second squared, times the time, 10 seconds. And so that is equal to 4.6 meters per second squared times 10 seconds, and that gives us 46, a nice number, meters per second. And that we are comparing to what we computed earlier here about the change in the magnitude of velocity, which was 13.10 meters per second, and clearly the magnitude of the change in the magnitude of the velocity vector does not equal the magnitude of the acceleration vector times time. 46 is not equal to 13.10, clearly. Why not? Well, because this is teaching us something about the math that we might have known already. The operatives, if you remember learning about things like commutation and distribution and those kinds of arithmetic properties, the operatives of the magnitude of the x vector and the change in the x component do not commute. Okay, so we're finished with our initial progression through this problem. By doing it carefully and deliberately, we have the answers to parts A, B, C, and D. But now, before we just walk away, we're done, let's do a reality check. We reign by surrender.
We reign by surrendering to Jesus and praying for our daily bread, which includes success
in our schoolwork.
God will answer and lighten our yoke and the impact of the thorns and thistles in our labor.
The final step in the idea problem solving format is the assess stage, which I referred to as a reality check. First, we want to check that our units make sense. So let's look back across the problem. We have a change in acceleration times time should give us a velocity, and we have units of meters per second, check. Going back to the change in the magnitude of the velocity vector, also meters per second, check. Our angles are in degrees, check. And you can go back to the first part of our evaluation and similarly make sure that the units that you end up with from the calculation equal the units that you would expect for a velocity or an acceleration. Okay, what about the sign and the magnitude now? So units, check. We can take advantage of the kinematic equations and just move them around a little bit and check our calculations that way. So the change in velocity in vector form is equal to the acceleration vector times time. And so we have the acceleration vector given to us, which was 2.6 meters per second squared. And the y component was 3.8 meters per second squared. That's our vector. Times time, which was 10 seconds. So we can multiply that through 26 meters per second and 38 meters per second are going to be the x and y components of the change in the velocity vector. Now, the initial velocity vector, we know. So we had computed the initial velocity vector to be 4 meters per second in the x direction and negative 21 meters per second in the y direction. So if we did that correctly, then the final velocity vector should be equal to the initial velocity vector, right, plus the change in velocity, all in vector form. So let's check that. We now have the numbers that we said were correct. Let's see if that works out. So we have the initial velocity vector, 4 meters per second, and negative 21 meters per second in the x and y components, plus again in vector notation, 26 meters per second in the x direction and 38 meters per second in the y direction. And we can add the x components and add the y components. And that comes out to be 30 meters per second in the x direction and 17 meters per second in the y direction. And that's what we had. That's what we were given as the final velocity vector. So that checks out. And we're done.
Written in the Word, in the good, good Word, is a message from our God. Gonna tell you all about how to get to the kingdom, the good life. Written in the Word, in the good, good Word, is a message from our God. Gonna tell you all about how to get to the kingdom, the good life. Oh, I love Jesus. La 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 la. Oh, I love Jesus.